Hello, welcome back. So let's move in our list of turbulence models in the flat plate case, Reynolds number 10 million. So K-Omega, we covered it, K-Omega SST, we covered it, and now we're going to cover K-Omega K-Omega 2006. Okay, so this is K-Omega family. It is Y plus insensitive. It's a very good model, I have to say. It is my favorite model. So let's address a little bit the theory, and now let's look, and then we look at the results. So let's take a look at the theory behind the Wilcox 2006 K-Omega Turbulence model. So as usual here, I have a few references. So we go back to the NASA Turbulence modeling website. So we go back to the Wilcox family. So we were in the SST. Now we go back to this one. And when you enter here, is the first one you encounter. Okay, you have the references here, equations and everything. So I have my own slides that I wrote down the equations, so it will be easier to understand, but it's pretty much the same thing that you have here: boundary conditions and coefficients and so on. And then you have many variants and versions of this model. Just to show you here, I have the reference paper also. So this is the paper, pretty much the same that you have in the NASA website. So I always invite to read this paper. There are very interesting comments there. There is, in this model, as you look at the model also, there is a version for compressible flows. So there is a different, instead of Reynolds averaging, it's a FAF averaging, but at the end of the day, we get the same. And your equations, and the difference, one of the difference between this model and the other version of the Wilcox and the SST, you have this called cross diffusion term, okay, and you have it here, and it's to reduce this sensitivity to boundary conditions. So you have this paper that talk about that, okay, so you want to understand more, but generally speaking, you have here the model, coefficients and so on. So if you look the mathematics, still there is a lot of mathematics, but it's less than the mathematics that you find in the K-Omega SST, that you have many blending functions and correcting functions, damping functions and so on, that can make it tricky to understand. Then you have boundary conditions, so formulation for rough and smooth walls. Then also you have mass transfer. So it's a very complete paper, very interesting. I strongly recommend it to read it. I enjoy a lot this paper, the cases, and I realized that this is a very good model, even better than the SST. This model, like the SST, incorporates this stress limiter. Okay, so sometimes the models in stagnation points tends to overproduce too much tourniqueted energy, so it's already incorporated there. And a lot to cover here, so many interesting test cases. If you want, now you can take your time and validate these cases. But also we know the physics, so by looking at the previous results, these functions and so on, we can know if what we're doing is correct. So that being said, let's move to my slides here and to address briefly the model. Okay, so one of the things of the model, and we have this remark by Wilcox. So an ideal model should introduce the minimum amount of complexity while capturing the essence of the relevant physics. So I completely agree with this statement, and it is true when you look at the K-Omega 2006 and then to the K-Omega SST, and you will see the difference, that the SST is very, very complex. Then the 2006, it will reduce that complexity, and it will and also it will capture the relevant physics not to the same accuracy as the K-Omega SST. So here you have the references, okay, and some comments here. So a brief summary of this model. As I say, it's a beautiful model. One of the things that you have that cross diffusion term, now just to minimize that sensitivity in free stream, but also there is a stress limiter now to improve results, transonic, supersonic flows and so on. So our equations talking about that term is this one. As you look, is always they are very similar. No, the K-Omega SST, they take the same form. What it will make it different, it is all the blending functions and damping functions implemented. So in this model, we compute the turbulent viscosity like this. So let's complexity if you compare with the SST, just to point out that the omega tilde is computed like this, but it still is less complex than the SST. Okay, or your coefficients, then the function here of this cross diffusion term, so say that takes different behaviors near the walls, far from the walls. This model, it will introduce no vorticity tensor. Okay, so somehow we'll see that it will have an improvement when you have separation and so on, this kind of problems. So here you have all the functions. Okay, and the only blending function that is used in this one is this one to control this behavior near wall free shear, but it still is less complex than the SST models. Like in previous models, from the variables K, omega, you can compute integral length scales, you can compute epsilon in this wall, and the values of your constants. Now, and as always mentioned, all the physics is contained in this constant or coefficients, no, because you can change it, okay, tweak it a little bit. So probably we'll prepare a video just to say a few words about that. So boundary conditions, as I mentioned, you have it there, you have some references, so it's up to you to get a good estimate of these boundary conditions. Remember that you have also free stream values. Okay, so those are estimates. Okay, so you should get something physically realistic. Okay, not far from realities. You put a crazy value there, likely it's going to diverge. And this is it. Okay, this is our overview of the model, and now let's get our hands dirty. So here we are in the folder for the K-Omega 2006, and let's enter there. Also, let me visit as well the folder of the turbulence models here, and look at that. You have the K-Omega 2006 here, and if you open the source code, you have the reference here, and sometimes, well, it's documented, sometimes you have some comments there and so on. So let's go here to the High-Ranus wall functions, and just to point out, we have the solution. I'm not going to run the case. Okay, so this to save some time. Okay, but I want to show you here Python plot watcher. There's the residuals. Okay, so what happened here using the wall function, and we have all our behavior continuity. Look at that. The variables became a little bit unbounded. Look at that K, it became negative, but very small value. So it's not a problem. Here you have your output, and on the screen what is happening. Okay, and your Y plus and so on, everything seems to be okay. So now let's plot our quantities. So as usual, I will open the scripts, the states. So the first state, okay, everything is okay there, and we have it here. Okay, as you can see, a good agreement. Hopefully, yeah, we are familiar with this kind of plot. And here, let me see that is kind of an ISO, that I have the other quantity there. So let me switch off that quantity, and also hopefully you will have the updated one. Let me save it. Okay, let me go here. Remember, well, also always look at this pipeline here. You will see all the steps now, but to remind you, what we're doing here is sampling in this line normal to the wall. We have the shear stress here, velocity here, and we construct this plot. Okay, so you will have all the steps here. This one will give you the wall shear stresses. To remind you, here I put it there, spreadsheet value, and here you have the value. Okay, the wall shear stress in that point. If you want to go to another point, just change the position. Okay, then you move here, and calculator one, you compute shear velocity. So let me see, it's the same values. Okay, and look at that, as you put another value, it would change. So this is telling you that if you are computing the wrong quantity, okay, you're not going to, or if you use the wrong boundary conditions, you're going to get the wrong wall shear stresses, and You are not going to match our theoretical result. And then you go here and keep reading, then compute the y plus value. Here you compute your u plus value. Here you compute your up lam value, your laminar. So this is for the plot here. Then you have the turbulent correlation and so on. Okay, so a standard. Okay, hopefully we visit this a lot, so I hope you are familiar with this script. So let me close here. Okay, we have an okay solution. Let's go to the next state. Okay, and delete here, open, load state, part of view, state 2. Okay. And there you go. We have the solution. Let me change this color here. So we have our total kinetic energy. We have the turbulent viscosity. You see how it's kicking in according to your y plus value. Remember that we're modeling everything below this 200. And here you have your shear stresses and so on. Okay. So let me also update this one just to make it clear so you know what quantity we're looking. So QOI is quantity of interest. So let me update this. So will be here beta star. So it will be this one. Okay, QOI 1. And there you go. Updated. And let me save state here, state 2. And here, nothing to comment. Everything makes sense. You can compare all cases. Remember, when we look here at node also, it should peak somewhere here in your boundary layer, like you see. So everything makes absolutely sense. No, we know the physics. Okay, validating the case without knowing all the experimental data or reference data. So now we move to the state 3 where we have that reference data. Okay, so it's very helpful if you have it, but if you don't have it, you have all the guidelines how to do that. Okay, how to do the validation. And I go here, and there you go. So we have our classic plot, the velocity profile, and the comparison with the friction coefficient. So another source bar, but also the correlation. And you see that we have a very good matching. And remember that SST that we have that strange behavior. Look at that, the 2006 doesn't suffer of that behavior. And to remind you what was happening here, okay, so if I go here, open this one, to SST, you have this strange behavior here. And here you don't have it. So you have something to think about, you know? So I call that a weightlifting snowman. So think about that. Okay, so there you go. So nice results. Let me close here. And now let's move to the low rep. Okay, but before moving, also to remind you, we have to set up boundary initial conditions, and look at that. Nothing changed. If you open this, nothing changed. Exactly the same combinations, values. Okay, it doesn't matter how you change your turbulence model, how you put the KQR or omega or epsilon, will be exactly the same. To you will be to choose the right numerical value. Okay, and remember also, if you go into constant where you have wall functions, it needs to be defined as a wall. So let me go here, and the wall is here, bottom. Look at wall. Okay, be careful about that. Also, for the script to save the production term, remember that it changed from turbulence model to turbulence model. Use it in OpenFOAM is called G. You have it here, K-Omega, in the wrong folder, by the way. Should be 2006. This one, this here, Control-D. And there you go. K-Omega 2006 G, and this will be the one that multiplied by K to get the dissipation, a specific dissipation rate. Okay, so we are there. Now we go to the low rep. We have a solution. Okay, Remember, boundary conditions, everything should change according to the guidelines that we have. Remember that now the numerical value for this one, as the mesh is much finer to the wall, this quantity will be large. In this case, accordingly, I corrected. You can open it. Probably the value I insert in there will be different from the one that you are going to compute using this correlation, because I add some correlations, personal experience. But remember, you need to get something physically realistic. So let's open the scripts here. Okay, and when I open here, now we're going to do exactly the same now, post-processing comparison. So we go for the first one. Okay, everything okay. And now we're wall resolving. Okay, so, and there you go. You have the whole behavior here. Everything here makes sense. I don't see any strange behavior here. Okay, this is how we, and to stress this one, I have repeat this in every single video, but just to, I want to imprint this in your brain. Now that if you know a physical behavior, and we know that this has been widely validated, this kind of behavior, if you match that behavior, you know that you are doing things right. Okay, I cannot say that your final result will be right. That only God knows. But you know that in the good road, you are taking the right assumptions, using the right conditions, and so on. Okay, so let me close here and let's go to the other state in PataView. Okay, load state, it will be this one, state 2. Here we have the production dissipation. Okay, and everything in equilibrium. Look at that, cool, very nice results. So here we have K and node. I like to put in this plot. Then we put here quantity of interest 1 and 1 in this axis, and we put the quantity. So here at the walls, you have this, probably the behavior is not perfect equilibrium, but then when it goes to fully turbulent here, everything is equilibrium and they balance out. Okay, there are many other, this is a budget of turbulence quantity. So I just put in here production and dissipation, but you can put many quantities. Okay, and when you do your balance, everything should conserve, should go to 0. No, you'll do the summation and so on. So everything seems okay. Now let's move here to the last one, okay, of these states. And there you go. Fantastic result. Okay, usual plot, velocity profile, nothing strange. And we put it here, perfect match now with our reference results. And let me put here now to compare also with the high ray. So to talk about now the advantage of using now. So look at the solutions, very good. So this solution takes half the time of this one. So this case is something that is quite fast. But if we talk about 40 million cells, you will see the difference and why many times we like to use wall functions. They do have limitations, so you should be careful. Later we talk about that, but generally speaking, if you don't have massive separation, they should work fine. Okay, so this is it. Okay, we compare with the K-Omega 2006, Wilcox fantastic model. And now let's do another test. So the test that we're going to do here, let's modify boundary conditions. And what I want to show you what happens, you choose the wrong values. Okay, so look at the, okay, where I am in the high ray. So actually let me work in the high ray. So I want something fast, I don't want to wait too much. And let's say that I want to, so you have these 3 boundary conditions and you can do whatever you want. I will go for K. Let me go for K and let me say that, okay, I will take this approach. I will put a fixed value there. I know it's wrong, but let's see what happens. Okay, so let me go here, cd HRR and run all. So probably will iterate, probably will diverge. So look at that, it's converging. No, it is iterating Maybe later it's going to explode, who knows, but I don't see anything strange there. But at the end of the day, when we plot the quantities of the wall, we see the difference. So let's wait for the solution to analyze these results. Okay, we have a solution. So I plot the residuals here. You see that nothing is strange, probably a little bit unbounded, the quantities, but the final truth here is when we plot the results. So to make things fast here, I will go to the Python folder and I will use the Python script, just to remind you that also you have this script. So you will need to go through the ParaView window now. So now we go here and there you go. So we have the solution. I don't see anything strange. So as I mentioned, this is one of those flukes that you get a good result. Okay. So, but let's say in theory it's not correct what we did there. So now let's do it again. And let me do like this. So let me put now this, and let me put a small value that is already wrong when you put a fixed value. But if you put a value of 0, is even worse, because that should be a large value. Okay, but it shouldn't change much. But let's rerun again this case. Okay, so it will be sh run all, and let me be 100% sure that I have that. Oh, because probably okay. Okay, we have the right setup, and let me also print this here, and let's wait for the final results. Okay, we have a solution. So we have our plot of the residuals here. As you look at the screen, nothing strange. Well, besides that, this quantity is becoming unbounded, but it's a small value, but since makes perfectly sense. So at this point, let's do the same here. Now we have everything. Let me go to the Python here and run this script, and let's see what happens. So hopefully, I hope to see the wrong results that already see here. And there you go. And this is what is happening when you use the wrong boundary conditions. Okay, so now in this case, when these results that we're getting, they are below this theoretical value, they are over predicting the shear stresses. And when they're above, they're under predicting. So they get closer to, let's say, this viscous sublayer correlation, the laminar one. So less shear stresses, more shear stresses. So later when we talk about boundary conditions, roughness, you will see that this profile is going to shift downward, but that physically is correct. What you see here is not correct physically. This is wrong, and you have seen due to the fact that you choose the wrong boundary conditions. Same can happen if you choose this the wrong numerical value. So let me go. This is okay, this is okay, and let's say that internal value, and let's put here 0. Okay, we might get the right results, we might get something slightly different, and let's go here also and let's use a different one. Okay, so this one, if we get different results, this is not going to be the responsible of that. Just to show you different approaches, that this one K, we're computing K, we can use it. So let's do the same. So let's go back, let's run with this setup, and let's see what happens here. Okay. Okay, so we have a solution. As usual, nothing strange here. You look at your output here, everything seems to make sense. Okay, so now let's post-process our results. So we go here, and let me go again to the Python folder here and use this script. So remember, what we did here is that we put a small value. Okay, we use the right behavior, and this is what we have. So as you recall the previous one, you will see the original one, that there is a better matching here, and here you see that there is a small deviation. Okay, so it's up to you to judge, but you start to see the influence of boundary conditions, and you can do the same with the free strings values, and you will see that influence. So main takeaway, choose wisely your numerical values for boundary conditions, initial conditions. Hopefully you have seen the dependence here and what can happen now according to the behavior. Okay, interesting case, no, very interesting case. You can change here, you can play around with these conditions, also see the influence, you can plot the profile, see if there are differences, and so on. To point out something about this Python script, automatically is also getting the wall shear stresses. So you don't need to do anything. Whatever you get here, it is correct. Instead of you use the state of paraview, remember that you need to sample the shear stress in that point and then recompute the shear velocity to get the right plops. Okay, that is the only difference. Okay, I'm not going to open that. Okay, what we were doing here. The final thing that I want to do here is just to show you something here in fvSchemes. Let me go here. It's this cert here. So remember, this is just for the Y plus insensitive turbulence models, the K-Omega family. So this is the way how you compute the distant normal to the wall. Now, to make it Y plus insensitive, you have this computation now. And if you misspell something there, okay, you are going to get now all the valid options, and see that here it failed. Okay, let me go for run. Okay, and why it's not computing? So where I am? Okay, and 2006. Okay. So let me go here, and okay, this is interesting because now that is this one doesn't complain. Okay, the 2006 does not use this quantity. This is interesting. Okay, but to show you, let me go to the K-Omega SST. Okay, high red. And let's go here in this one, and okay, you always learn something new here. I didn't pay attention to that. So fvSchemes, and to go here, let me misspell here, and phone run. And this one will tell you this is the patch distance method, and there you go. You have these three methods. So the one that is recommended is the mesh wave. Okay, then you have advection, diffusion, and Poisson. Poisson is a fantastic one. I like it, but you need to have good quality meshes. This is trickier to implement, to use, and probably this is the most general one, so most of the time I go for this one. But stay with this one. If you want to use something different, go for the Poisson. Remember, Poisson, you need good quality meshes. Now, the skewness, if you have a lot of skewness, it will give you problems. This one, honestly, stay away from this one. Okay, so that's the last thing that I wanted to show you, and just to be sure that everything is okay. So there you go. Now we play around with boundary conditions. We look at different options. We look at the behavior, what happens when you choose the wrong combination of boundary condition, even the numerical value. These low Reynolds are even more sensitive to the numerical value. So you can go to this one, and if you go to Omega and you put here a low value, you would see that the profile now is not going to be correct, probably similar, but you're going to see those differences. So know your theory, you have our template there, to use just to get better estimate according to your quantities, your inlet velocities and so on. But there you go. You have your template, your way of validating everything, okay, by comparing with the behavior that we know of the physics. So let me go here and another method down, okay, and many more to go. So let me cross it here. So this punk is covered. We have another punk that is this one. So I'm going to show you this one in this case, but this model belongs to the scale resolving simulation. This is something that you're going to use for 3D on a steady, but in this case it's going to work as well. Then we have one more bandit of the K-Omega, which is this one. Okay, this is transition model. Okay, so I will leave that to the end. So we have two bandits here when it comes to transition: K-Omega SST, Langrid Menter, and KKL Omega. These two we're going to address in this case at the end. Honestly, I don't know if they're going to give right results. Probably yes, probably no. But also we have a specific case for transition to turbulence. Transition to turbulence, it is the most difficult thing in turbulence modeling. It's very difficult to capture. The models are specific for that, very well calibrated models. So later we'll visit that. So hope you are enjoying this playlist, this CFD cookie, and see you in the next videos. Bye.